Conduction. Conduction is the process by which heat flows from the hot end to the cold end of the body due to temperature difference without any actual movement of the heated particles. When one end of a metal rod is placed in contact with a flame, while the other is held in with hand, the end being held becomes hotter and hotter, although it is not itself in direct contact with the flame. The transfer of heat continues till two ends of the object are at the same temperature. This method of heat transfer is called conduction. Those solid substances which conduct heat easily are called good conductors of heat. For example, silver, copper, etc. All metals are good conductors of heat. Those substances which do not conduct heat easily are called bad conductors of heat. For example, wood, cloth, air, paper, etc. Thermal conductivity. Thermal conductivity of a solid is a measure of the ability of the solid to conduct heat through it. Suppose the one end of a metal rod is heated. The heat flows by conduction from hot end to cold end. As a result, the temperature of every section of the rod starts increasing. Under this condition, the rod is said to be in the variable state. After some time, the temperature at each section of the rod becomes steady, that is constant. Temperature of each cross-section of the metal rod is maintained constant but not the same. This is called steady-state condition. Under this condition, the temperature at points with the rod decreases uniformly with distance from the hot end to the cold end. The fall of temperature with distance between the ends of the rod in the direction of flow of heat is called temperature gradient. Temperature gradient is equal to θ1 minus θ2 upon x, where θ1 is temperature of hot end, θ2 is temperature of cold end, x is length of the rod. Coefficient of thermal conductivity. Consider a cube of each side x and each face of cross-sectional area A. Suppose its opposite faces are maintained at temperatures θ1 and θ2. θ1 is greater than θ2. Under steady-state condition, the quantity of heat Q that flows from hot face to cold face is directly proportional to the cross-sectional area A of the face, that is, Q is proportional to A, equation 1. Directly proportional to the temperature difference θ1 minus θ2 between the two faces, that is, Q is proportional to θ1 minus θ2, equation 2. Inversely proportional to perpendicular distance x between hot and cold faces. Q is proportional to 1 upon x, equation 3. Directly proportional to time t in seconds for which heat flows, that is, Q is proportional to t, equation 4. Combing all the factors from equation 1, 2, 3 and 4, we have Q is proportional to A into θ1 minus θ2 into T upon X. The quantity of heat flow from hot phase to cold phase is Q is equal to K into A into theta 1 minus theta 2 into T upon X, equation 5, where K is a constant of proportionality and is called coefficient of thermal conductivity. Its value depends upon the nature of the material. If A is equal to 1m square, theta minus theta 2 is equal to 1 degree centigrade or 1 Kelvin, T is equal to 1 second, X is equal to 1 meter. Then from equation 5, Q is equal to K. The coefficient of thermal conductivity of a material is defined as the quantity of heat that flows in 1 second between the opposite faces of a cube of each side 1 meter, area of cross section 1 meter square, and the faces being kept at a temperature difference of 1 degree centigrade or 1 Kelvin. Unit of K. Therefore, thermal conductivity of a material is given by K is equal to Q into X upon A into theta 1 minus theta 2 into T. In SI units, Q, X, A, theta 1 minus theta 2 and T are measured in joule, meter, meter square, degree centigrade and second respectively. Unit of K is equal to joule into meter upon meter square into degree centigrade into second is equal to joule per second meter degree centigrade or joule per second meter Kelvin. Since joule per second is watt W, the unit of K can also be expressed as watt per meter degree centigrade or watt per meter Kelvin. Coefficient of thermal conductivity. Rate of heat flow in the cube is given as Q upon T is equal to K into A into theta 1 minus theta 2 upon X. Equation 6. The quantity Q upon T is the time rate of heat flow, that is, heat flow per second from the hotter phase to the colder phase and is at right angles to the faces. Its unit is W, watt. In terms of calculus, the above equation is written as dq upon dt is equal to minus k into A dq upon dx, where d theta upon dx is equal to temperature gradient and negative sign indicates that heat flows towards the direction of decreasing temperature. Determination of coefficient of thermal conductivity. Experimentally, Dr. G.F.C. CERN used the equation Q is equal to K into A into theta 1 minus theta 2 into T upon X to calculate K. Conditions necessary for this method are: a measurable amount of heat must flow through the bar conductor second. The temperature gradient along the conductor must be steep enough so that it can be accurately measured.